So shall we start?
Yes, yes. I think we can start now. Good, good morning, everybody. This is the sixth day of the workshop. I invite our resource person, Professor Vishnu Nandidiri, to start this session.
Good morning, all of you. And today we are going to continue with the discussion that we started yesterday. So we were discussing a few topics from the module called the sympy that's available in Python. That's a symbolic Python. So there we try to define certain variable names, symbols, and try to make use of that because we know that in mathematics, what happens is that many of the times we usually play with symbols without assigning any concrete numerical values to them. For example, whenever we are talking about sine x, that x is a variable, and most of the times we will consider that to be just a numeric quantity or something similar to that, and we multiply them. Sine x into sine x into x, we write it as sine x square. Sine x plus x, we write as sine 2x. All these things we do playing with the symbol x. And similarly, we try to define many symbols, and most of our formulas are in terms of symbols like the quadratic expression, the general formula, the general form of a quadratic equation. We say that ax square plus bx plus c equal to 0, where a, b, and c are real numbers. Even there, a, b, c, and a, b, and c, even though they say that they are real numbers, we usually represent them. We usually just keep them as symbols, allowing the possibility of giving some value to this A, B, and C. Therefore, symbolic manipulations or symbol manipulations are very essential in many of the fields in mathematics. So the symbolic Python module is actually meant for that. And even for differentiation, even for integration, all these things, we usually differentiate variables without assigning any, without evaluating any particular value, without evaluating the expression at any particular number. We try to evaluate the integrals without making it definite. That's indefinite integration. So at all these places, the symbolic expressions are very essential. Okay. So the module symbolic Python is essentially used for taking care of all these kinds of higher level mathematics, higher level, or maybe we can say mid level at least, because high level, I don't know exactly. We can call these things to be in the high level. This is definitely not in the low level because we will be trying to differentiate, we will be trying to integrate, we will be trying to manipulate certain. We have already seen some series expansions. We will be trying to find roots of the equations. These are not certainly low level. Maybe we can call this to be the medium level kind of mathematics. If we divide the mathematics into lower level, mid level, and high level, maybe we are discussing all these things related to in the medium level of mathematics. In case in the sense of difficulty. Okay, so we are continuing with our discussion on SymPy. I will try to introduce more and more functions, features from SymPy through problems so that we can easily understand, we can easily identify that where this particular idea can be actually used. Okay, let me start sharing my screen. In Spider, once again, if you are using Google Colab, you can open your Colab interface if you are already signed into your Google or Gmail account. So let me share the Google document for pasting the code first. Here it is. Okay, let me start my Spider interface. Okay, the Spider interface is here. So let us try to introduce something new today. Yesterday itself, we have seen factorizing polynomials in terms of linear factors we observed yesterday. And we have seen that if we specifically give some field, like specifying the extension or specifying the extension to be a field consisting of all the roots of that particular polynomial, we can factorize any polynomial into any polynomial. I'm not saying exactly the correct thing. That's not completely true. Any polynomial just like that cannot be factorized always, because we don't know whether such a factorization actually exists, whether such a formula actually exists or not. Of course, roots are there, but roots may not have any closed form. Okay. For every polynomial, we know that over the complex numbers, of the set of all complex numbers, we can find roots. Linear factors there do exist, but the difficulty is that the linear factors may not be rational numbers. They may not be even algebraic numbers. If they are algebraic numbers, there is a possibility that we can express them in terms of radicals. Okay, solution by radicals for every polynomial does not exist. But that's why one of the foundational reasons of Galois theory, because not foundational reasons, but one of the what you call consequences of Galois theory, that radicals with the degree, polynomials with degree greater than or equal to 5 cannot be, there cannot be a closed form formula for solving all such polynomials with degree greater than or equal to 5. For some polynomials, it may be possible, and there exist some polynomials for which closed form roots in some closed form cannot be expressed. Okay, so don't expect Python to solve every polynomial for you, Python to solve every equation for you. But most of the times, whenever solutions exist in terms of radicals means square roots, taking some power, taking some 1 by some power. All these things, not many times it may exist, but whenever it exists, Python usually will be able to find out this using the symbolic Python module. And whenever such closed form formulas do not exist for the roots, we will move towards finding approximate solutions using numerical methods. For solving equations, expressions in mathematics, it can be done in exact way, or it can be done in an approximate way. For approximate way, we need to seek the help of numerical analysis. That's the only way. And that branch of mathematics we will discuss later after completing the symbolic Python related stuff. Let me start a new program first. So this is the 30th program that we are going to have. Okay, the very first command that we will try to introduce is the solve command. I think yesterday we have seen factor, expand. I think these were the major things that we have seen yesterday. Now today we are going to have something called a symbol. We have seen symbols. We have seen. Now we are going to see solve equations using symbolic Python. Okay. So for this, let us import symbol and the solve function. Okay, there is actually, you might be actually wondering that. So in SymPy, there are several functions available. Is there any way to import all of them in one command? There is, of course. We can use this command, import star. If you use this particular line command from SymPy import star, so whatever function is available in SymPy will be automatically coming into our what you call interface, or our particular program. But the problem with doing this particular problem with executing such a statement is that we don't exactly know that what are the functions available in SymPy. We may not even remember. There are many. So if you are using this from SymPy import star command, the problem is that uh, we might have defined one particular function in our own program. That function name may be, say, factorial. SymPy also may be having a function factorial. Once you are importing using a star command, wildcard statement. This is something called wildcard importing. Wildcard is star. So that means that import everything. If you are importing everything, the problem is that SymPy factorial function and our own factorial function may have some conflict. So which one is going to work? We don't exactly know because our factorial function may be slightly different from what actually the sympy is defined. So in which way it's going to work is not very sure. Therefore, importing everything using this command is not encouraged. This is not actually a good practice. So you should import only those modules, only those functions which are actually required for you. Okay, you should know exactly that what you are importing and why you are importing certain. Here, even here we can see in Spider there is one comment. Symbol is important but unused. Symbol solve is important but unused. This will actually give you some hint in your problem that you are importing something you are not using, but provided that you are importing using the names. If you are importing using wildcard, there is no such hint available anywhere. Okay, so don't use this. You should not use this. It's better to avoid this. From sympy import star. From math import star, that's also possible. From com c math import star, possible, but you should not do that. You should clearly know that what you are exactly importing and why you are exactly importing. Only those things you should import. Okay. So the solve is important. Now let us define it and a symbol x. Remember that whenever you want to use x as a symbol, x as a variable name, you should define it always as a symbol. Otherwise, the problem is that Python will be treating this x as a variable name, requiring some numerical value inside that. In Python, a variable is defined only after assigning some value to this. Okay, here you are going to assign x the value of symbol x. Assigning the value of symbol x. Done. X is assigned a value. Now let us define a polynomial, or directly also we can do. No need to do it like this. Suppose that we define. Suppose we solve a simple equation. 3x or 3x. Most of the times in mathematics we write 3x, but in programming language this is not correct. You need to there is nothing called 3x. You need to separate them using star or some other arithmetic operator you should apply. 3x plus 2. So essentially what we are trying to do is we are trying to or equation, even though this is not an equation, what we actually mean is 3x plus 2 equal to 0. This is what we are trying to solve. Now solve equation. Solution 2 equal to 0 is, let us do some formatting. Equation solution. So neatly formatted. 3x plus 2 equal to 0 is, what is this O? Okay. Is minus 2 by 3. See that this is the solve actually gives a solution as a list. Let us put this to be equation 1, so that we can try to solve something more. Equation 2 can we try some complex thing? 3x plus j, 1j. But when we are moving to this complex domain, what happens is that everything is evaluated as a decimal entity. Everything, the final solution is appearing as a decimal number. 2 by 3 is going to be 1 by, what's happening here? 3x. Okay. Here it is 2 by 3. Here it is I by 3. This is correct. Double. So complex number also it can be solved. Now let us do take one more equation. can it solve the sine function? So sine x equal to 0, will it solve? Let's see. But sine is not important. I don't know whether sine is available already in the sympy library. Okay, from math, import sine. Just try to see it's working or not. Oh no, sine this is requiring. Okay, let me just try to see if sympy is available here. Okay, so this is what I told. So if you are importing everything from the math library, then sine also will be imported. If you are everything from sympy using the wildcard command, this sine is once again imported. You don't know what sine is going to work because the sine in the math library requires a real number as the argument, whereas sine in symbolic Python can even take Sine and symbolic Python can even take symbolic arguments. Sin x is equal to 0 is here solved. And the solutions are given to be 0 and pi. Because I think it's looking for the solutions from the 0 to pi domain. Okay, it's looking for the solutions from the domain 0 to pi. Cos. You can even directly do that without requiring these things. Cos x or say cos square x, cos square x minus 1, which means that cos square x is equal to 1. Okay. Cos square x, you cannot give cos square because cos is a function, you cannot do like that. Cos of x, the whole square, that's the only way. Minus 1. So we are trying to solve cos square x minus cos x is equal to 1. Sorry, cos square x is equal to 1. Let's try. 0, pi, 2 pi. Even e raised to x, I think you need to export exp as the function. See that? Exp of x. Exp of x is equal to 0. Okay, let us try with exp of x is equal to 0 first. So the solution is an empty list, no solution. What about 1? Solution to exponential x minus 1 equal to 0 is 0. See that this exponential of x minus 1 equal to 0, this equal to 0. Equal to 0 is actually given here by this particular expression, double equal to 0. In the actual expression, there is no equal to 0 or anything like that. It is simply solve exponential x. Simply solve exponential x minus 1. Okay, let me update the Google document with all these things. The link I have already shared. So I have updated the Google document. You may try. So solved. That's it. Now these are all. Initially we have seen linear equations. So what about solving quadratics? Okay, let us try to even see that. Non-linear. This should not be different anyway. Suppose that we try to solve x square. X is already a variable name. X square minus 2x. Once again, most of the times, what happens is that since we have the experience of writing 2x, we straight away do the same thing here, 2x. But remember, we should type 2 star x plus 1 x square minus 2x plus 1 is just 1. So what about x square plus 1j x square plus 1, not 1j, x square plus 1. Unexpected intent. Where is the intent? Oh, we haven't closed the bracket. Minus sign, plus sign. So it is showing those. It is giving complex roots as well. Now, can we solve in terms of more symbols? Suppose that we have x square equal to a or x square minus a we want to solve, and we don't know what exactly this a is. How do we do that? Once again, define a to be a symbol. Solving x square plus a. Let us try to see. I don't know if it will work. Now there is a small problem that here we are asking for some solution, but asking for solution in terms of what? That's the question. Because there are two symbols in this particular equation. So next, this equation is with symbols a as well as x. So solution in terms of what? We want to solve for what? Solve for which variable? Solve for all the variables or solve for just one variable? So maybe we can say that the solution is required in terms of x. Sorry, solution is required for x. We are trying to solve this for x. Okay, when multiple symbols are involved in an equation, we should clearly mention that we are going to solve it in terms of what? Or if we solve it in terms of x, if we solve it in terms of a, the solution is this. Okay, now let us derive the quadratic equation formula. That's minus b plus or minus b square minus 4ac by 2a. Can we do that? Let us define b and c to be symbols. But for that, you need to import from sympy. Either you need to use the symbol command multiple times, or we can use symbols. bc equal to symbols bc. Okay, now let us quadratic equation. Quadratic equation is not completely correct because we don't have equal to sign in this expression. But remember that, just keep in mind that we are actually going to solve this expression equal to 0. A x square plus b x plus c. solution for the quadratic equation you want solution for x. Minus b square root of b square minus 4ac appearing in reverse order by 2a minus b. Oh, so this is minus of, sorry, the minus is taken outside. So minus b plus square root and minus b minus square root by 2a. So quadratic equation formula also can be derived like this. Let me update the Google document. So after the exponential, I have not done. Okay, updated the Google document with the codes. So you can try with your own expressions if you want. So the only thing is that the functions, mathematical functions available in the math library and CMAT library are not compatible with the sympy symbols. So if you want to use those and find a solution involving mathematical functions like log, etc., then you need to import the corresponding functions from sympy library. You cannot use the functions from the math library or CMath library. That may not work. So let's try to see. The logarithm function is clear to us. We know that the logarithm function. So remember that logarithm to the base e. Suppose that we are asking for logarithm of say some number, logarithm of 10. So essentially what we are asking is that for getting 10, e should be raised to which power? Okay, that's essentially the meaning of asking the logarithm of something. Okay, so logarithm of this is natural logarithm. Once, if you do not specify any base, that's the natural logarithm. Logarithm of y to the base b is equivalent to asking to which power b should be raised to get y. Okay, logarithm of 100 to the power 10 essentially means that to which power 10 should be raised to get 100. And so the answer is 2. Okay, what I wanted to say is, so how do we find anti-logarithm in Python in that case? How do we find anti-logarithm? So what is meant by anti-logarithm? Logarithm is nothing but 10 to which power we need to rise. Anti-logarithm is reversing, right? So e to that number. Suppose that a number is given. Okay, what is the anti-logarithm of it? By definition. Okay, let us try to solve it. So let's import the symbolic Python function from symbolic Python logarithm function. Import log. So if you want some help on log to see how it's working, you can ask for help after importing. You'll get a lot of things. Examples are also there. All these things you can see. Okay, now let us try to solve something. So suppose that we try to solve log x to the base 10 is equal to 2. Sorry, minus 2. So anti-logarithm of 2 to the base 10. So anti-logarithm of 2 to the base 10. This is actually the anti-logarithm calculator. Maybe we can write a function also. Something like this. Define. So what do we require? Anti-logarithm, if we assume that we are taking the base to be equal to 10 all the times, so we just require x sympy. We need to import log because we are writing a function, therefore it's better to import whatever addition required in import these things inside anti-log itself. Import log. So what is next? Our expression is log. What are we trying to solve? X 10. Oh, sorry. This is some value, so y. We need to import symbols and define x to be a symbol. Y is here anyway. Y is a numerical value. Solve it. What to solve? Solve the expression. There is only one variable because x is the only one variable. Y is a numeric value. Solve it. Return solutions. Let's try to see that. Anti-log is maybe we can say that anti-logarithm to the base 10 of 2 is should put a bracket also to make it neat. So function we have to find. Three is 1000. So we have defined an anti-logarithm function using sympy. Sympy can be used for calculating anti-logarithms. So let me update the Google document with this. Up to quadratic equation is updated. Where is the quadratic equation? Okay. See, the definition of the function need not be on the top of the file. The only thing is that if you are defining the function in the middle of the file, then you can use that function only after that. Okay, not just in the middle of the file. Wherever you are defining the function, only after that the function definition can be used. That's it. The Google document is updated. Okay, this is how we can solve equations as well as expressions using symbolic Python. And they have also seen, okay, now suppose that we have a multi-variable equation. Suppose that we have equations involving more than one solution. And in fact, if we have an equation, if you have a formula, then we can use the same formula to find out. Suppose that a formula, suppose that f of xy z is equal to f of xy. Okay, that means that z is equal to f of xy essentially means that z is expressed as a function of x and y. Now, suppose that you want to express y as a function of z and x. Um, of course, it's not going to be possible all the times because there can be, if the y term appearing on the right is in some power other than 1, then it may not be all the times possible. But if it's possible, symbolic Python actually can be used for even performing formula reversals or function reversals, or finding essentially if a function is expressed in terms of a formula, the inverse of the function can be found using a symbolic Python solve. Okay, that's possible. Inverse can be found. For example, we know that y square equal to 4x. Y square equal to 4x corresponds to its equation of a parabola. And there we are actually expressing x is equal to y square by 4. So essentially that's a function of y. Suppose that we want to find the corresponding inverse function. Since inverse function does not actually exist there in the pure sense, because y square equal to 4x means that corresponding to y square equal to 4x means that corresponding to two values of y, there will be exactly one value of x. Okay, corresponding to 1 and minus 1. Plus and minus, the x values are going to be exactly the same. Anyway, we can try that. Parabola. Is y defined anywhere? Okay, let me define y equal to symbol y. Just use the same print statement once again to save some typing. Multiple symbols are involved there. So y square equal to 4x. So this can be okay. If you solve it for x, the solution is going to be y square by 4. Okay, x is equal to y square by 4. Okay, solving for y, what do we get? So for y, we are actually getting this as two branches are there, minus 2 square root of x plus 2 square root of x. Okay, that's correct. That's perfect because it's expressed in terms of x and y. Sorry, it's expressed in terms of square root of x. There are two branches corresponding to this particular square. So even this is possible. Functions can be inverted, reversed, but provided that, of course, if it's possible. So even system of equations also can be solved. Okay, system of equations also can be solved. So solving system of equations essentially means that we are trying to solve two equations at a time. So inside solve, we can put two equations at a time. That's quite possible. But now, on the other hand, suppose that if you have a single equation and involving two variables, and if you're trying to solve, what will happen? That also we can try. Single equation, two variables. For example, x plus y is equal to 0. Okay, and solving for x and y both. X plus y. So what's the? Of course, if you solve for x or y, you will get the other way. But we don't. We want the solution to be in terms of x as well as y both. Or we need not specify that properly. So the solution is x equal to minus y is the solution, it says. That's it. If you specify x and y, what will happen? Minus y, that's the solution. Is it correct? X is equal to minus y is equal to y. So if you want to clearly know that what exactly is meant by that, which variable corresponds to y and which variable corresponds to minus y, then you can turn on the dictionary option. In that case, x is equal to minus y is the solution. Okay, that's it. So now let us try to solve um, a system of equations, suppose. So system, equation 1. Suppose we put 2x plus 3y equal to 0, 5x 6y. I think this is solvable because, yeah, they are not multiples of each other, so must be solvable. So let us solve. Solution 2. So multiple equations. So what are the equations? System of equation 1, system of equations 2, solving. We need to enclose this sys eq1, sys eq2, undefined name sys eq2. Okay, this is also given as 1. Okay, correct. eq2, solve both. Let us not put the dictionary there. Okay, try to see. There are multiple, so we need to be a little bit more careful. Expression 1, one more bracket is required. Okay, the solution here is x equal to 0, y equal to 0. Okay, naturally expected because this is invertible. This is invertible. Solution becomes equal to 0. Okay, let's try instead of this. Suppose we will put 1 minus 2. What will happen? 0, 1 by 3. It's giving solutions anyway. Minus 6, 16 by 3. So suppose we put them to be linearly dependent. 2x plus 3y. Okay, suppose there are, okay, if there are no solutions, it will simply print an empty list. Okay, if there are solutions, then only it will print. Suppose that we take them to be linearly dependent, then 2x minus 3y, keep it to be 0, and 4x 6y minus 2. Let us put it to be minus 2. So what will happen? Also, this is empty. Yeah, here the solution is appearing to be x equal to 3y by 2. So it's appearing correctly. There's no problem. So linear algebra equations can be solved like this. So how far I have updated the Google document up to finding antidog. Okay. I hope that up to here things are clear to everyone. Now, um, we can actually create a program in which we can input. Suppose that we want to accept input as an expression. So, if you want to accept input as an expression involving variables, then you need to be a little bit careful. You need to convert that expression into something that symbolic Python can handle. Okay, let's start a new program for that. I think this program has already become 102 lines, of course, with some empty blank spaces here and there, but still, let's make a new program. Accept symbolic input. So essentially, what we are trying to do is that suppose that we have uh, a system of equations to solve, and suppose that we want to solve it using symbolic Python, and we do not want to write the program entire equations inside the program, but instead of that, let us try to accept it from the user. Okay, so it's a variation of this. So maybe I can just copy these from here. Let me save this first. Remember, I need to always define symbols. Whatever symbol I'm trying to accept, I should define it. Also, not the case, the difference between symbol and symbols. Symbol is using S as the capital in the beginning. Symbols is using everything small. Now enter a linear equation in two variables, x and y. So that's the message that we are showing. Linear equation 1, linear equation 2. Okay, let's try to take care of this later. So two expressions are now entered. Now the problem is that, as I told previously, that the input is actually taken as a string, but we want, even though we are giving the input as 2 star x plus this 3 star y, that will be treated only as a string. Now we need to convert that into a symbolic Python expression. Okay, our work is actually to convert that into a symbolic Python expression. Just 1 second. So converting, just I'm just trying to find out something. Okay, for that, let us try to use simplify for that thing. So our aim is essentially to accept an input. Okay, let us try to accept the input. Now, if you run this, what happens is enter a linear equation. Suppose, okay, before that, equation 1, equation 2. Let me stop it and run it again. So suppose that the first linear equation I'm trying to enter is this 2x plus 3y. Suppose I enter 2x plus 3y. Suppose I enter this also. So x and y are treated to be 2x plus 3y, x is equal to what is happening here? What is the equation I gave? Okay, so the value is given to be x in terms of 3y 2. Here, even though we have given the expression as a string, sympy automatically, because it understands that x and y are defined to be symbols, it converted this x and y automatically into what do you call, automatically it took the x and y entered inside a string as symbols. Okay, it automatically took care of that thing. Okay, let us try to do something more. Quadratic equation, let us try to input. Quadratic equation, input. Let us try to define all the variables A, B, C. No, we don't want A, B, C. We want a concrete solution, so we are not going to define that. Enter a quadratic equation. So wait for the equation and solve it. Let us see in X. Solution to 0 is quadratic equation. Solve the quadratic equation. There is no need of any dictionary here because there is only one variable. Okay, let me comment out the previous things because this is not necessary now. I'll turn it on afterwards. So suppose I enter a sympy expression like this: x square minus 2x plus 1, and the solution is 1. Okay, even here it's working. So the thing is that if you are entering a symbolic expression as a string using input, sympy is capable of understanding what exactly it is. There is no need to do any such conversion. I was thinking that conversion is required, but here no conversion is actually required. So you can straight away use it. So these are different programs, but I have anyway combined them. So let me just copy this to Google document. Oh, I have not updated after anti-logarithm, the previous one. Okay, let me update the previous program first. The previous program is now completely updated. Now this program is also updated. I have updated both the last one as well as this one. I forgot to update the previous one. Now it's done. You may try. In fact, symbolic Python can provide LaTeX output. Okay, that could be useful sometimes while writing some programs, while trying to expand some polynomials. It is probably better to get some LaTeX output, and it can actually expand even trigonometric functions. Okay, let us try to do something related to that. Some certain things, basic things in symbolic Python. So let us try to accept or try to expand. In fact, let us try to expand something. So expanding polynomial products. Suppose that we have polynomial 1 equal to, we need to import symbols first. X and Y are symbols. Polynomial 1 is x plus 3 the whole cube, and polynomial 2 is x plus y the whole square. If you multiply these two, product of, or otherwise straight away, star equal to. So let's do the format, put the arguments in format. Polynomial 1, polynomial 2, star 2. Okay, so let us expand it. It's not expanded, it's shown exactly like that. Expand is not defined, so import expand. So the expansion is here. Now there is actually one special function available in sympy. Let us see it in action, and after that I'll try to explain. This is a very old function. I don't know whether it's going to work this time in the latest versions of sympy. Let's try it anyway. No, oh, this is not required. So after that, run init printing. This is just an open close bracket. There is nothing else. And now see the output of this. If I am succeeding in that, I will try to explain. No, there is not much success. Init printing is turned on. No, it's not much useful. So I'm not trying to expand. I think it's in the spider interfaces is not working. Most probably this will work in another interface called IPython. Even though we are on the right side, we seems to use IPython. It's not exactly like that. This is a console like thing. Somehow I wanted the output to be formatted a little bit more beautifully. That's not happening. So I'm not trying to explain that here. So let us just don't worry about that thing. So instead of that, let me try to find out. Let me try to find out the LaTeX code corresponding to this. So this is the expand command. After that, we see if LaTeX expression can actually be found out. LaTeX code for the product is this. Removing these two. LaTeX code for the product is X to see that this is actually the corresponding LaTeX code. See, on the other hand, here it was shown to be x plus was shown. X to the power of 5 was shown in the Python way, but here it is shown in the LaTeX way. Here 2 star extra is the good thing with this is that if you are performing some computations in something, and if you want to copy and paste if you want to make use of that output of that computation directly into your LaTeX file, you are typesetting something, you want to make use of that directly. So instead of typing it again, instead of modifying it again, you can ask Symbolic Python to provide the LaTeX, the corresponding the output in LaTeX format. Output in the LaTeX format. Now one more probably. LaTeX code 4. So if you are solving, how do you get the LaTeX code? If you're solving something, how will you get the LaTeX code for that? Okay, let us try to see. I think where we had done that, the quadratic equation solving. Is it here? Here it is. A, B, C. Let's see the LaTeX code corresponding to this quadratic equation. Solve. So the solution is appearing as a list. So you cannot directly, I don't think that you can directly apply LaTeX code into this, but instead of that, let us try to print the solutions one by one. So see that the solutions are listed as solutions are actually listed as a list. So solutions are. Let us now for each of the solution, where is the solution saved? So let us save the solution into some variables, and we can loop through the variables. Solutions is this for yes in solutions, print LaTeX yes. So what will happen? The solutions are fraction minus b plus backslash square root minus 4a. See that? These are the two solutions. Minus b plus square root of b square minus 4ac is of course b square minus 4ac is listed in the reverse order, doesn't matter, by 2a, and this. Now you don't have to type the corresponding LaTeX code or modify the code to fit into your LaTeX file. Straight away it can be done using the LaTeX function available in sympy. See that the Python symbolic Python actually helps you to import the result of your computation directly into your what you call LaTeX file, so that you don't have to do anything extra. Once you found a solution using Python, you can straight away use that in your file. And even minus pi and pi also can be printed like that, just exactly like that in LaTeX. That's what I think. Okay, I have not tried. Okay, let us see that even when minus pi etc. are involved in the solution, will it be okay? Since square root is coming out, that also should from sympy import sine. I'm solving sine x equal to 0 or just sine x. See that solutions are appearing as backslash pi corresponding to pi. So this is the good thing with using LaTeX functionality in Python. Let me update the Google document with this. The previous one was it updated? Just try to once again update it. Okay, done. So updated everything else up to now, up to here. Yeah, one more is that you can expand even trigonometric expressions also can be expanded. That's one thing that I want to just tell. So, for example, suppose that we want to expand sine 2x plus 3y, for example, or sine 2x itself. So for that, sine x plus y to start with. Have I imported sine? Yes, I think yes, sine is already imported. The symbol y, okay, y is also here. If you try to expand this, what will happen? Sin x plus y is just given us sin x plus y. If we expand it, no. So simplifying, trying to simplify. Okay, but the extra thing is that we need to give here the problem is that it's not understanding that what exactly we want. So we need to specify an extra parameter here, saying that the simplification, the expansion, not simplification. Simplification is not really necessary here. So the expansion needs to be done. Uh, need to be taken, need to be provided as trigonometric functions. That's right. So the formulas also can be recovered using Python. Sin 2x in terms of simpler functions. Cos 3x can. So only thing is that the trigonometric argument must be kept and it must be set to true. Now, I think a few things were actually left out before going into the next thing that we have to discuss is something related to plotting. But before going into that plotting part, probably I should SciPy solving equations is already done. Working with expressions is already done. Something the complex number related things were left out. So only a few very basic things are left out in the case of complex number things. Let me just try to finish those things also today before going into plotting, because plotting can be even done, I think, summing series, solving single variable, limit of function, continuity, area. These things, no further plotting is there anywhere. The plotting can be taken as a single thing tomorrow. So let me just try to do something related to this symbols plotting. So a little bit of complex, a little bit more about the complex arithmetic, dealing with the complex arithmetic. Let me update the entire thing in Google document first. So updated the entire file in Google document. Now I'm starting a new file. So more complex. Okay, recall that the complex number previously we defined using the symbol, using the format a plus bg. Okay, complex number in the usual Python programming, the complex number can be defined only using the symbol j. But when you are using symbolic Python, the outputs are coming as I. So if you're using symbolic Python, maybe you can even use I. Okay, we'll try to see that. Anyway, the complex number is defined like this: is that 1 equal to 2 plus 3j, and I think print type is that 1. So this is complex number class. Trying to define z2 equal to 2 minus 3j, and trying to print the product of these two, star z2 should work perfectly. It's appearing perfectly. Now sometimes it may be necessary to get out the real parts of certain numbers, imaginary parts of certain numbers, but for that what do we need is, okay, let us try to this is 0, 2 plus 3j, so let me put uh, 3 minus 2j, product z equal to, let me mark it to be under this, printing the product. After that, trying to see the real part, imaginary part, real part, real part is this, imaginary part is this. So finding the real part, product is that. Oh, we need format, real. So dot real, dot imaginary. think this is not necessary. This bracket is probably not necessary. Try to do that. Trying to move it. Yeah. Real part is 12.0 and the imaginary part is going to be 5.0. Now, the conjugate also should work. And in fact, we can convert a number into complex directly by using, suppose that how do we input a complex number? So how do we input a complex number? Maybe directly inside the program, you can just type it to be a plus bj. And one more thing is, instead of typing a plus bj, you can just use the complex class, complex converter, complex 5, 6 if you use, or 5. Pi is available there, I think. 5, pi by 2. Then if you use this, okay, the pi is there. And if you use sympy, even then 5 is appearing like this. So you can define a complex number like even this. So you need to specify only the x part and y part. So the structure is z equal to complex x, y. That's it. Now to find out the argument of that. Argument of that is in the sense that suppose that xy coordinates are given. Argument is just the angle which it makes with the. Suppose that we are drawing a line from that particular point to the origin. The angle in the angle in the counterclockwise direction that the line joining origin and that point makes with the x-axis. That's what the argument is. So to find out the argument, for example, suppose that we are defining it to be 0. Suppose we define the point to be what? Point to be 0, 1. Okay, or 1, 1. I don't know if this is a command to work. So, okay, face is the command that we should use. Face. This is C math itself. C math. Face or angle. This is the way to do that. Zero point 0.78. 1 point, I don't know if 0.78 is actually okay. To be clear enough, let us try to use this. 1.57, 0 and 1, that's on the y-axis, which is a distance of 1.2. Okay, I think it's pi by 2. So this is correct. So you can find the angle like this. Angle the point makes with the x-axis in the counterclockwise direction. So the phase can be used. Well, of course, on the other hand, you can find the tan inverse also. arctan 2, where is it appearing? Okay, arctan cannot actually be used. So this is one way, and instead of that, if you do not want to use phase, you can directly define uh, because you know that the point is nothing but it's equal to r cos theta and r sin theta. Maybe you can even try to do that, but not necessarily. Phase can actually be used. So now using phase also, you can define a complex number. You can define the using magnitude and direction also. You can define a complex number just by using. So to define a complex number using direction and magnitude. So just use sine and cos, and we know that this is r cos theta and r sin theta. Right? Z4 equal to complex, whatever your r is equal to 2, say 2 cos at an angle of pi by 2, or at an angle of, yeah, pi by 2 itself we will use pi by 2, 2 cos sine pi by 2, or even make it simpler, pi by 2 here, so that you can use cos t sin t. So what is this number? This number should have been what we expect the number to be. The number is 2, 02 is the number that we expect, 02. Is this correct? Yeah, because 1.22 etc. into e raised to minus 16, some approximation is happening there. That's why all these confusions are happening. So 1.22 etc. Into e raised to minus 16. E raised to minus 16 is it's as close to 0 plus 2j. Because of that 2 sine theta, we are getting 2j. So a number can be defined. A complex number can be actually defined in this way also. So this is another way. So complex number can be defined in any of these ways. And the conjugate also can be defined the same way. Conjugate can be computed, not defined, computed. Conjugate of these. So which number should we take? So product is, let us take conjugate of this is that spelling is wrong. Sorry. So conjugate of 12 plus 5j is 12 minus 5j. And the absolute value or norm can be found using the product. Since norm is real, You need to just take the real part and put brackets properly, because the imaginary part is 0, but even then it will be printed. So otherwise, if you try to convert it into, okay, that's not necessary. You can find out the conjugate like this. Okay. And if you do not even want this, maybe you can find the absolute value. Oh, sorry, I forgot to take the square root. I took only the square. That's not the norm. Square root and apply the real part afterwards. So using the absolute value directly, it can be used. Now, can we directly type something? Okay, that's not really necessary. Accepting the complex number input can actually be done using, um, maybe you can get it as a comma b and then probably convert into C math or something similar to that can actually be done. Okay, I think most of the things related to complex number arithmetic also we have covered. Now, as I told, the thing left is about, okay, the feedback link. Yeah, see here. Let me update whatever we have typed into the Google document. So it's updated in the Google document. Now there is actually one more technique available in Python for treating rational number as a rational number instead of converting it into numerical value. So for that you need the rational function. So, for example, suppose that we have a rational number. Oh, okay. From sympy import rational. So after that, we can convert any number to its rational format, rational form of Suppose that we have 0.5. So we can do like this. Now, on the other hand, suppose that we are trying to convert some pi into rational form. Even then it's working, because the thing is that the 3 point, see, this is something that we need to understand about how computers are treating, even though symbolic expressions are there. So the rational function tries to convert this pi, the symbol, into a numeric value, and that numeric value is of course an approximation. So every approximation, it's a finite expansion, finite expression. So it's converting that finite expression into a rational expression. So actually, by we have actually committed a kind of blunder here, because we have converted pi into a rational number, which is not quite. It's not going to be anywhere true. So here we are trying to convert the pi into a rational number. Python says that this is the rational expansion, the rational expression corresponding to pi. But what might have happened here, what actually happened here is that pi is initially converted into a decimal expression, because in computer everything is finite. The decimal expression also is a finite thing. So corresponding to the finite thing, a rational expansion is strong. A rational expression is strong. Don't think that pi is rational. Okay, we're not proving that pi is rational. We cannot. Okay, I think that's it about the symbolic Python, complex arithmetic. Certain things were left. Rational function from symbolic Python, LaTeX we have completed. Now the only thing remaining in this part, this symbolic Python part, is something related to plotting. The plotting function is available in two major big libraries in Python. One is the matplotlib, which is again enclosed inside SciPy package, and the plot is available in the symbolic Python also. There is no basic difference between these two in the way in which the commands are working, but the only thing is that for certain symbolic computations, you may need to use the plotting function available in the plot library. Okay, that's the only difficulty. There are certain confusions like this, because Python was enlarged to include most of these mathematical functions in several stages, not in one day. So there can be inconsistencies. There can be same functions appearing in different libraries with seriously differing features. All these things are quite possible because it's an open source software. Contributions are coming from different side. So I think with this I will stop today's session. Tomorrow also we will be having the session at 10 o'clock itself. And if there is any question, you may please ask now. I can try to clarify.
No questions? So we have, I think we can stop now. Any doubt? Any doubt? So we have successfully completed 6 sections of our program. I thank Professor Vishnu Nandaviri for even in this holiday he is spending for us. Thank you, sir. I also thank each and every participant for their sincere participation.
Is there any question? Somebody has raised their hand. If there is any question, you may ask now. As I told, even in the beginning of next day, also you can get doubts clarified if there are any. Okay. Okay. Thank you very much for your patient listening, and we will meet tomorrow again at 10 o'clock, right, ma'am?
Okay. So tomorrow, please join before 10 o'clock. 10. That is better. So that we can start our session sharply at 10 o'clock. 10 a.m. Okay.
Okay.
Thank you.
Okay. Thank you.